is the Paris equation. It's used nowadays still a lot to describe the crack growth of long cracks. However, there are several problems with it. It is an empirical equation, so there's no physics behind it, and it is dimensionally correct only when you change the dimension of the constant with a change in the exponent. And for your simulations, the cycles to failures depends very much on these two parameters. So you want to have these two very accurately to have a good simulation for your lifetime. So usually this is what you do. This is the test. So you plot this on a log-log scale, and then you fit your Paris equation, and then you get your C and N parameters. However, sometimes you can also plot it a little differently depending on how the data is, how much data points you have. You can fit it also like this. If you have two samples, you get different numbers, and when you combine them, you can make a master curve. But also, the information is lost from multiple samples. So it's not always convenient, it's not always the best way, I guess. So the question, the initial research question was, is there a correlation between the constant and the exponent? There's been a lot of debate about that in literature. So if you just, this is one sample, you get a constant and you get an exponent. And for multiple samples, you get multiple combinations. So is there a correlation? And if it is, if there is a correlation, then the constant is dependent on the exponent. So if that is the case, then you can write the Paris equation to a relative crack propagation law, and you get a dimensionally correct equation of this kind. And what does that mean? It means that you get different exponents, and that you get a pivot point over here. So there's a lot of discussion in the literature. Is there a pivot point or not? And if there is a pivot point, it allows to describe the crack growth rate only by a variation in the exponent. So if you do multiple tests with the same stress range, and you substitute the n for 2m, then you can rewrite this to an equation like this. So the stress is out, and we make this just an equation from the crack length. So in the next slides, I will present only or plot everything against the crack length here. So this is the only, just crack length, which is in there, and it's also in beta squared. There's also crack length dependence on that. So what we did was we did 29 middle tension tests on 70-75 plate material with only one stress range, with a maximum stress of 80 megapascal and 0.1 stress ratio. And we had an initial crack size of 2 millimeters. And here you see the results. This is I only plotted 5 here, but this is the one with the minimum number of cycles to failure and the maximum number of cycles to failure, and all the other curves are in between. But as I mentioned, I only plotted 5 here. So what we noticed was that from about 10 millimeters on, all the curves are the same. So this difference is the same as here, and it also applies for all the other samples. So all the variation is caused by crack growth in this up to 10 millimeters, from 2 millimeters to 10 millimeters. And from there on, the crack growth rate is the same. And it also implies that the constant and the exponent are the same at that point, from 10 millimeters on. So when I plot here, as I mentioned earlier, I plot it against a b squared, which is similar to delta k squared. And I only plotted here the one with the least number of cycles to failure and the most number of cycles to failure. And this is the crack growth rate. And we see that it intersects, and that we can model it with two different exponents. So here we have a pivot point, and as I mentioned, this is at about 10 millimeters, and from 10 millimeters onward you get the same rate and also the same slope, and we can quantify it with it's 1.85. So this is now the model that we use to describe the samples. So we only have one parameter left, and this is the exponent here. For this one, for the crack growth rate beyond 10 millimeters, everything is fixed, and below 10 millimeters we only can vary the exponent, and that is what you see here. So you can choose the slope here, and otherwise everything is fixed. So this is the model, and these are the curves, and you can see the model is the dotted line, and you can see all the models are on top of the measurements. And when you go to only 2 millimeters to 10 millimeters, here you can see these you can fit the crack length data, not the derivative of that, but you can really fit the crack length and obtain the exponents for every sample. So this is not, this is already known, it was already observed in 1967 that there was a knee in the crack growth rate at this point here, and that was present for nickel, steel, titanium, all these materials. So it's not only aluminum, it's for more materials. And they stated that it was due to a change in exponent. The change in exponent was due to a change in the stress state. So you go from plane strain to plane stress at the knee. So at this point here. And we also observed that. So this is the fracture surface looking on top of it. So this is the slanted 45 degree area here. So it's due to the lighting that we take a photograph with the lighting, that this is darker. And here you can see it from the side, so you can see the shear lip coming in at that point. And when you look where it starts, it is on average at about 10 millimeters. So also in our case, we could see that the change in exponent was due to the change in stress state. Zuidema at the TU Delft already also observed this knee in the crack growth rate and related it also to a change in stress state. However, they investigated it and they saw that the shear lip is not responsible for this change, but the mechanism behind the shear lip is probably responsible. And we think that it is the change in the plastic zone size, so really the volume, that is responsible for this change. So you get, this is the plastic zone size in plane strain condition, and here you go to a different volume in plane stress. And it is thought that the change in volume is responsible. And we also see that for other materials. So when you go from very brittle material, where you have, so this is aluminum oxide, you have very low plasticity, and you have a very high exponent. And when you go to ductile materials, you go to a lower exponent. So there appears to be a relationship between the number of plasticity around the crack tip and the exponent in the parallel-sheet equation. So this was my conclusion. So the model, we could model the crack growth with two different exponents using a dimensionally correct equation. And we could model all the differences between the samples with only one change in one parameter. And it also allows us to determine the constants with a very high accuracy. And we think that the plastic zone size or change in plastic zone size or volume is responsible for that. So that was it. Thank you very much.